begin with, we're asked to express 1 over x minus 1 times x plus 2 all squared in partial fractions. So we let 1 over x minus 1 times x plus 2 all squared equal a over x minus 1 plus b over x plus 2 and then plus c over x plus 2 squared. Multiplying all through by the x minus 1 times x plus 2 all squared gives us 1 on the left hand side. Multiplying a over x minus 1 by x minus 1 times x plus 2 all squared, the x minus 1 will cancel and we're just left with a times x plus 2 all squared. Multiplying b over x plus 2 by x minus 1 times x plus 2 all squared, one of the x plus 2's cancel and you're just left with b times x minus 1 times x plus 2. Multiplying the c over x plus 2 all squared, x plus 2 all squared will cancel and you're just left with c times x minus 1. If we now fit in a value of x equal to 1, the left hand side will be 1, and then on the right hand side we'll have a times 1 plus 2 all squared, which is 3 squared, so that's 1 is equal to a times 9. The second and third terms here, because x equals 1, will disappear. So this then enables us to say that a is equal to 1/9. If we now put x is equal to minus 2 into the equation, the left hand side will still be 1. The first term will disappear because it's negative 2 plus 2, which is 0. The second term, the b times x minus 1 times x plus 2, will disappear, and the only term we'll have is the c times minus 2 minus 1, which is minus 3c. So if minus 3c is equal to 1, c is equal to minus 1/3. Finally, if we put x is equal to 0, then the left hand side will be 1. This term here will be 0 plus 2 squared, which is 4 times the value of a. Value of a is a ninth, so that will be 4/9. So 1 is equal to 4/9, and then fitting in 0 here is 0 minus 1 is minus 1, times 0 plus 2 is 2, so that's minus 2 times b. And then finally, putting in 0 in this last term, c is negative 1/3 times negative 1. That will give us plus 1/3. If we now rearrange this, we can find what b is. 2b will be equal to 4/9 plus 1/3. 1/3 can be written as 3/9, and then subtracting the 1, which is 9/9. So 4/9 plus 3/9 is 7/9 minus 9/9, so 2b is equal to negative 2/9, which gives us that b is equal to negative 1/9. So we can write our partial fractions. 1/9 for a, but we can put the 9 in the bottom with the x minus 1, so that's 1 over 9 bracket x minus 1. b is also a ninth, negative 1/9, so we can also bring the 9 down the bottom, so that's negative 1 over 9 bracket x plus 2. And the third term, c is equal to negative 1/3, so we can subtract from this a 1 on the top, and we can put the 3 in the bottom with the x plus 2 all squared. And there's our partial fractions. For part B, we're asked to obtain the general solution of the differential equation. So we've got x minus 1 times dy by dx minus y is equal to x minus 1 over x plus 2 squared. First of all, we'll divide all through by x minus 1. First term will be dy by dx. The second term will then be minus 1 over x minus 1 times y. On the right hand side, when we divide by x minus 1 will just leave us with 1 over x plus 2 all squared. If we now look at this, we see that this is the form of an integrating factor type differential equation. We've got dy by dx and then a function in x times y is equal to a function in x on the right hand side, and I'll label this the right hand side because we'll be using it later. To find the integrating factor, we find e to the integral of what's in front of the y here. So that's e to the integral of negative 1 over x minus 1 dx. To do this integration, we'll bring the minus 1 outside the integration, and this will just be minus the integral of 1 over x minus 1 dx, which is log. So this is minus log of x minus 1. So this is e to the negative log of x minus 1. This negative is a negative 1, and by the third law of logs this can be taken in and made a power. So this then becomes e to the log of x minus 1 to the power minus 1. Now since e and log are inverse functions, the answer to this is just x minus 1 to the minus 1. The integrating factor is x minus 1 to the power minus 1, or 1 over x minus 1. The solution to the differential equation will then be given by the integrating factor times y is equal to the integrating factor times the right hand side that I pointed out earlier. So that's y times 1 over x minus 1, or y over x minus 1, is equal to the integral of 1 over x minus 1 times the right hand side, which was 1 over x plus 2 all squared. So that's the integral of 1 over x minus 1 times x plus 2 all squared on the bottom. And this was from part A. We put this into partial fractions. So instead of this integral, we can separate this into 3 integrals based on the 3 partial fractions. So the first of those integrals will be 1 over 9 times x minus 1 dx. The second partial fraction, giving us a second integral, is minus 1 over 9 times x plus 2 dx. And the third one was minus 1 over 3 times x plus 2 all squared dx. Integrating the first of these, taking the 1/9 outside the integral sign, we're then just left with the integral of 1 over x minus 1, which is log x minus 1. Doing the same with this, only this time it's a negative 1/9, we get negative 1/9 log of x plus 2. The third integral won't be a log because it's an x plus 2 all squared. What we'll do with that is bring the minus 1/3 outside the integration and take the x plus 2 all squared up to the top to become x plus 2 to the minus 2. Now this last bit, integrating, we have got minus 1/3. Now integrating the x plus 2 to the minus 2, add 1 to the power and divide by that new power, that'll be x plus 2 to the minus 1 over minus 1. Because we've got a minus third outside, this will end up as a plus 1/3 times x plus 2 to the minus 1. But x plus 2 to the minus 1 we can write on the bottom along with the 3 as an x plus 2 to the plus 1. The first two of these terms we can combine because we've got a common factor of 1/9. Inside the brackets would be log x minus 1 minus log of x plus 2. Second law of logs tells us that we can make that the log of x minus 1 over x plus 2. So our first term here is 1/9 times the log of x minus 1 over x plus 2 plus the 1 over 3 times x plus 2 plus c. Now this is y over x minus 1. To find what y is, we would take the x minus 1 and multiply it by the whole of the right hand side. And this is our answer, our solution to the differential equation. For part A, we're asked to prove by induction that cos theta plus I sin theta in brackets to the n is equal to cos n theta plus I sin n theta for all integers n greater than or equal to 1. In other words, prove de Moivre's theorem. Start off with n is equal to 1. The left hand side will be cos theta plus I sin theta in brackets to the 1, which is just cos theta plus I sin theta. The right hand side will just be cos 1 theta plus I sin 1 theta, which again is just cos theta plus I sin theta. The left hand side is equal to the right hand side, so the result is true for n equals 1. We now assume the result is true for n is equal to k. In other words, that cos theta plus I sin theta in brackets to the power of k is equal to cos k theta plus I sin k theta. We're now going to try and show that cos theta plus I sin theta to the k plus 1, the next value up for n, is equal to cos of k plus 1 times theta plus I sin k plus 1 times theta. We can very easily get the left hand side correct if we multiply by cos theta plus I sin theta on both sides. So cos theta plus I sin theta to the k times cos theta plus I sin theta on the left hand side is equal to cos k theta plus I sin k theta times cos theta plus I sin theta on the right hand side. The left hand side is then cos theta plus I sin theta to the power k times cos theta plus I sin theta to the power 1. We add the indices. So the left hand side is just what we want it to be, cos theta plus I sin theta to the power k plus 1. On the right hand side we can multiply out the brackets. Cos k theta times cos theta plus I sin k theta times I sin theta, which is I squared sin k theta sin theta, multiplying the two inner terms I sin k theta times cos theta, and finally the two outer terms I cos k theta times sin theta. The I squared is minus 1. So this is just cos k theta minus sin k theta sin theta. And then plus I sin k theta cos theta plus I cos k theta sin theta. These first two terms form the expansion of the cos of one angle plus another. So this is the expansion of cos k theta plus theta. The second is just the expansion. Once you take out a factor of I, this is the expansion of sine of k theta plus theta. K theta plus 1 theta gives us an extra theta, a k plus 1 times theta. So the right hand side is just then the cos of k plus 1 times theta plus I sine k plus 1 times theta. This is exactly what we want to show. This is the result for 1 power up for k plus 1, n equals k plus 1. So we have shown the result is true for n equals k plus 1 whenever it is true for n is equal to k. Since we also showed earlier that the result is true for n equals 1, we know that the result is true for all natural numbers by induction. Part B, we're asked to show that the real part of this division is 0. On the top, we've got cos pi by 18 plus I sine pi by 18 to the power 11. Using de Moivre's theorem, or part A, we can write this with the 11 brought in multiplying the angle. So this is cos 11 pi by 18 plus I sine 11 pi by 18. Doing the same in the bottom, the 4 can be brought in to multiply the angle. 4 times pi by 36, the 4 cancels into the 36 9 times. So in fact on the bottom we've got cos pi by 9 plus I sine pi by 9. Dividing these two complex numbers, we subtract the angles. Pi by 9 can be written as 2 pi by 18. So the answer to this is the cos of 11 pi by 18 minus 2 pi by 18 plus I sine 11 pi by 18 minus 2 pi by 18. Subtracting 11 pi by 18 minus 2 pi by 18 is 9 pi by 18. So this gives us cos 9 pi by 18 plus I sine 9 pi by 18. But 9 pi by 18 is just pi by 2. So this is cos pi by 2 plus I sine pi by 2. Cos pi by 2 is 0. Sine pi by 2 is 1. So this is just 0 plus I times 1. The real part is 0. Imaginary part is a plus 1i. So we have shown that the real part of this is 0.